Well, I thought we'd take a look here in EET 260 microcontroller applications at some of our motor our motor type things. And so you can see I've got this program. I can also go, I believe, over here. And this is the first program I'm going to run. It's from Chapter 4 of What's a Microcontroller. And it's a basic stamp program. You saw I had a basic stamp, and what it's going to do is it's going to just continually run the pulse out 14 command with a value of 750. Now, these stepper motors want to see a pulse out value, and each one of these counts here is worth 2 microseconds. So this would be a 1500 microsecond or 1.5 millisecond pulse. And the way the positional servo works is that compares to a halfway point on the potentiometer that's built inside the servo motor. So in this program, all we do, it's called servocenter.bs2. All we do is send out the command to put the servo at half its position. 1500 is the full position, 0 is the minimum position, although you can't actually use 0 with a pulse out command. 1 is the smallest number you can use. And so based on that, the width of the pulses you send out, which is again is controlled by this number here, where you multiply this by 2 microseconds to get the width of the pulse that you're putting out. And so you continually do this, and the servo is supposed to go to its 90-degree position. So before I will download that program and run it, and we'll go back here. So my document camera is under the Macintosh side, and I'm running the PBasic editor over on the Windows side. So I think that's I'm sorry about that. But now this is, you can see my servo motor here. The little horn, or whatever you want to call this thing, is pointing straight up. That's the 90-degree position, and that's this thing has inside of it a motor and a potentiometer. And the way that potentiometer is wired up is, if it sees 1.5 millisecond pulses, the motor will drive you to that place on the potentiometer, and it will compare the 1.5 millisecond pulses where you used pulse out with a 750 value. It'll compare it to an internal pulsar that's going on inside of here using the potentiometer, and when they line up, you're at 90 degrees. And they're designed to line up with a count of with a count of 750 or a 1.5 millisecond pulse. Now, I hope to be able to show you on an oscilloscope that we are getting pulses out of there. Just to see if I can hook up my scope between ground and P14 is being used to drive the servo. So if I plug this into the P14 area, and I can currently this, I guess with the pulse out command, it puts out a pulse about 45 times a second. And let's see if you can see my oscilloscope over here. Not the greatest view with all that light coming in from the window. But what the oscilloscope is saying is the oscilloscope is saying 45 hertz, and you can see the pulses right here. They're not very wide, and if I were to kind of zoom in on these time-wise, or use my cursors or measurement function, I'm going to use a measurement function here, and I'm on source 1, and the type of measurement I'm going to use is a let's first look at pulse width. We'll get that in there, and then we'll add another type of measurement called duty cycle. So right now our pulse width, I don't know if you can see it here, I will try to focus. Our pulse width is very close to 1.5 milliseconds, and the duty cycle is it's only 6.7%. That is to say, the waveform is high about 1/16 of the time that of the period of the entire repeating waveform. So that's the 90-degree position. And I really should come up with some better way to show the oscilloscope. But you can see that that's what's going on. This program's running constantly. If we were to modify that program, let's say we wanted to go to the 180-degree position. This servo just goes from 0 to 180 degrees, or something like that. Again, you can't actually put a zero code out. So if I put 1500 in here and I reload this program, you may have heard a little buzz there as we go over. You can now see that the servo motor, and my servo motor isn't perfect on the 180 degrees, but it goes from 90, it was 90 here, now it's over here at 180 degrees. Also, I believe this servo motor rotates backwards from the parallax servo motors. This is from a SparkFun kit, so if yours rotates the other direction from mine, then I apologize. I have one maybe from a different manufacturer, but the guts are the same. They still have a potentiometer and a motor inside and a little circuit to compare your pulses with what the potentiometer says. And it creates a reference against which your commands can be compared. And that, by the way, is the very definition of a servo mechanism, is a mechanism that you enter a command, and the mechanism watches what it is you're trying to move or do or change the temperature of or whatever, and places it at the commanded position, watching with feedback. In this case, the little potentiometer that's buried inside this thing is the feedback, and it basically goes to a commanded position, and that's what a servo mechanism does. Feedback is a necessary part of that. So now we'll try a couple other different programs if we can, and this program called point2directions.bs2 we'll run for a time. This counter variable is a for next statement. It says for counter equals 1 to 150. So 150 times it'll issue the pulse out with a 1000 value. That should put us at the 3/4 position, or 135 degrees, or now that's supposed to be 1030 in a parallax servo. In mine it will be 130. When that's over with, it'll then move to do the same thing, but put it at the 1/4, I'm sorry, 2/3 position. This isn't 3/4, it's farther. It's I don't think this is 130. This is a slightly different number, but it'll put it kind of towards 1030 and 130. So we'll see how that happens. But again, my servo motor is backwards, so bear that in mind. And we will download that, and you can see it went to the 130 position and then 1030. Okay, and I wonder if I can. There it is at supposed to be at 1030, but it's at 130. Now it's at 1030. It's supposed to be at 130. So mine rotates backwards from the parallax servos. Again, what's happening is we're sending a series of pulses that are determined by this pulse out command, and the pulse out command takes this number, multiplies it by 2 microseconds. So the pulses in this case, if we were to run this continually, the pulses should be the pulses should be 2 milliseconds long. And if we want, we can just make up another program to show that. I'll take this code and I'm going to create a new program. I'm going to call this we'll call this 1-30-servo.bs2. How's that? And this will point to 130. And I'm going to just make this go continuous, like our servo centering, like our servo centering program did. We're not going to just run it for a while. So if I run this program now, my my servo runs to about 130, and if I look at the oscilloscope, once again with my clumsy mechanism here, if I look at the oscilloscope, you can see that it says very close to 2 milliseconds there, and our duty cycle is now 8.8%. That's right there. Our frequency is still about 44 times per second. And so that's just a little accident there. That's off camera. But, this is what happens when you kludge things around like this. Sorry. A little bit of live action here, as the Turtle Man used to say. Yeah, that'll get cleaned up. All right. So, never mind the man behind the curtain. So now, to kind of close out the demonstration here, I'm going to run one more program, and it's called point commanded direction, and I'll put this into the Blackboard Learn site as well. And what we'll do is we turn on an LED and say, hey, it's okay to enter an angle number 0 to 180. We then turn off the light. We compute the pulse command from the angle, and you'll see that that seems to work on this microcontroller, but it's certainly not perfect, or on this motor. Then we type out what the pulse command is, so you can see how it got computed. And then kind of like our two direction program, we will run from 1 to 250, and we'll pulse out our computed pulse command, and we'll pause 20 milliseconds, and so we should see our command going out. Now let's load this. And what's going to be kind of tricky here, let's put in 90, and I'm going to hit the 90 command, and we got 751, so we should be back to 1.5 milliseconds. And our servo is back to that 90-degree position. That's great. And our screen is gone for some reason. Let's see how we only ran the command for a little while. So in order to see this on a scope, I guess I'll have to run the command for a longer time. So instead of for 1 to 150, let's say for 1 to 500, and we'll send this down there, and we'll type 90, and we'll go over here, and you can see that we have our 1.5 millisecond and about 6.6 duty cycle. That ended, but it put the servo where we wanted it. And now we can type something like, well, let's say we want 45 degrees. Okay, so we type 45 degrees, we slide over here, and we see that we're down to 3/4 of a millisecond. Okay, and let's see, well, that went away, but 3/4 of a millisecond, and we're down even half the duty cycle, 3.4%. And now we're at 45. Now you can see it's, for some reason, this servo motor seems to go down below 0. So maybe there's a gain adjustment or something I could do if I knew what I was doing. But so let's just call that 45 degrees. And if we were to go back here and say that's 45 degrees left of 90, let's go 135 degrees, which is 45 degrees right of 90. And we go over here, and once again we take a look, and now we're at about 2.25 milliseconds and 9.6% duty cycle until it ended. And that's how we got that sort of thing. And we're at 135 degrees, a little farther than 135 degrees. So the servo is, I'm treating it like the command gives a linear angle, and that may not be the case, but it allows us to command this thing to go to a position and check its own feedback internally and say, I'm at that position and I'm going to stay there. And that's that's like I said, a true servo mechanism in how it works. So that's the positional servo motor. Just thought I'd do a little demonstration of that to kind of refresh you on how they worked. And you can see that in some vehicles nowadays, if they don't do the dashboard meters, fuel tank and temperature and speedometer and everything, if they don't do those graphically on something, they will actually use these inexpensive little servo motors, and when you start your car up, you may see all the needles go to the minimum position, the maximum position, and then come back to where they're supposed to be. And that's this sort of thing happening. Why do that? If you can make the servo motors cheap enough, it means you can do that all electronically, and it gets rid of the old mechanical cables that for and mechanical actuators that may have driven like your speedometer and that sort of thing. So anyway, with that all being said, that's our little demonstration on positional servos.